All right, let's just jump right into it. Have you ever stopped to think about what's actually making up the entire universe around us? Today, in this explainer, we're going to peel back the layers of reality and dive into the fascinating, totally invisible building blocks that create literally everything you know. We are getting into the basic concepts of chemistry.
I mean, just look around the room you're sitting in right now. How do scientists actually figure out the exact ingredients of a reality that we can't even see? It feels like magic, doesn't it? But really, it's just a beautifully structured system of observation. Okay, to build our intuition here, let's actually start with what chemistry doesn't care about. Your feelings, like love or hate, they're not physical stuff. You can't put a pound of love on a scale, right? But the phone in your hand, the water in your glass, that absolutely is stuff.
So that brings us to matter, which honestly is just the fancy scientific term for literally anything that has weight, takes up some amount of space, and interacts with our physical senses. Basically, if you can touch it, taste it, or feel its mass, it's matter.
Now, this matter can physically change states, and it's a simple chain of cause and effect based on how tightly its particles are gripping each other. Think of a solid desk. Those particles have a super strong attraction and are rigidly packed together. Loosen that grip a bit, give them some space, and you get a flowing liquid. And when they completely let go and have practically zero attraction, they become a freely roaming gas.
So, when we study all this matter, we divide its properties into two totally different camps. First up, physical properties. These are things you can observe without changing what the substance actually is, like watching an ice cube melt or just noticing the color of a rock. But chemical properties? Those describe how a substance reacts and transforms into something entirely new, like a piece of wood burning away into ash.
But here's a huge problem. The world is massive, right? So if I decide to measure a table in inches and you measure it in centimeters, we're going to have a total communication breakdown. How do we fix that on a global scale?
Well, scientists got together and solved this by agreeing on just 7 base SI units. This is basically the universal toolkit to measure absolutely everything in the universe. We use the Kelvin for the temperature of a star, the kilogram for the mass of an apple, the meter for length, you get the idea. It is the ultimate unified language of measurement.
Speaking of measuring things, here is a totally mind-bending difference that trips up so many people. Mass versus weight. Listen, your mass is just the constant amount of stuff inside you. It literally never changes. But your weight? That's just an effect. It's the shifting force of gravity pulling on you. So your mass is the exact same on Earth and the Moon, but your weight changes because the gravity changes. Crazy, right?
All right, but what happens to our math when we zoom way, way down into the microscopic world? I mean, the number of molecules in just 2 tiny grams of hydrogen gas looks like this staggering 24-digit nightmare of a number.
Seriously, how are we supposed to realistically work with a number that gigantic? Or on the flip side, decimals that are impossibly tiny. You lose your mind counting zeros, and missing just one zero could ruin an entire experiment.
Enter scientific notation. It is a brilliant shortcut. Instead of writing out 20 zeros and getting hand cramps, we just compress these massive strings of digits into a really simple multiplier of 10. You literally just grab a number between 1 and 10 and multiply it by 10 to a specific power. Boom, done.
Here's a quick mental shortcut to remember how this actually works. When you move that decimal point to the left to shrink a massive number, your exponent power becomes positive. Think of it as walking a positive happy path forward. But if you have a tiny fraction and you have to move the decimal point to the right, your power becomes negative, kind of like facing negative obstacles. Left is positive, right is negative.
Okay, let's take this math back into the real world, into the lab. Imagine 3 friends measuring the exact same piece of wire. Why might their answers vary by tiny, tiny fractions of a centimeter? Like one gets 2.00, one gets 1.99, and the other gets 2.01. Who's actually right?
The wild part? They might actually all be right, depending on their specific instruments. This proves that every single real-world physical measurement has a tiny, inescapable margin of doubt built right in. Nothing is perfectly precise, so scientists have to account for that uncertainty using what they call significant figures, which is basically just a structured way of recording numbers to show exactly how confident they are in that measurement.
So, okay, we've tamed the math, we've got our measurements down, but what is all this stuff actually made of? When we zoom right past the limits of human vision, what is sitting at the very, very bottom of matter?
When you really strip it all down, every single piece of matter breaks apart into these distinct atoms and molecules. They basically connect together like microscopic building blocks. Water, carbon dioxide, the screen you're looking at right now, it's all just a specific arrangement of these tiny, invisible spheres. And it was a scientist named John Dalton who really laid down the ground rules for this totally invisible world. His atomic theory basically said, hey, matter consists of these indivisible atoms, and atoms of a specific element are completely identical to each other. When they form compounds, they lock together in these perfect fixed ratios. And the coolest part? During a chemical reaction, atoms are never actually destroyed. They just reorganize themselves into new patterns.
To really wrap your head around how strict these rules are, think about the law of definite proportions. Imagine you get some water from an expensive RO filter, some from a basic kitchen tap, and some straight from the crashing ocean. Honestly, it doesn't matter where it came from. If it's purified, the chemical makeup is always perfectly fixed. H2O. 2 hydrogens, 1 oxygen. The source literally never changes the recipe.
Then there's Avogadro's law, which honestly reveals just a stunning symmetry in nature. Check this out. If you have 2 identical 1-liter containers of completely different gases, say hydrogen in one and oxygen in the other, and they're kept at the exact same temperature and pressure, they will magically hold the exact same number of molecules, no matter what the gas is.
But hang on, this raises a huge practical question, doesn't it? If we know these atoms combined in these perfect fixed ratios, how do scientists actually count them out in a lab to run an experiment? I mean, you can't exactly buy atoms one by one at the store.
Well, just like you intuitively know that a pair is 2 shoes, or a dozen means exactly 12 eggs, chemists just invented their own massive grouping system called the mole. It's the official SI unit for the amount of a substance representing a standard enormous batch of atoms or molecules. It lets a chemist weigh out a simple pile of powder on a scale and know exactly how many atoms are sitting right there.
Now, I really want to emphasize why this matters. Learning all these invisible rules, it is definitely not just some dry academic exercise. It's the exact blueprint that chemists use to synthesize literally life-saving compounds. By knowing exactly how atoms reorganize and how to measure them precisely in moles, we can create targeted drugs like cisplatin for cancer therapies and AZT for AIDS patients. This invisible math absolutely saves lives in the real world.
Which kind of leads us to a final mind-blowing thought to wrap up this explainer. If measuring and understanding the atoms in just a single drop of water gives us the power to literally save human lives, what other incredible secrets are waiting for you as you dive even deeper into the chemistry of the universe? Thanks for exploring this with me today, and definitely keep questioning the invisible world around you